Part 10, the Grassfire algorithm and harmonic gestalt. The Grassfire algorithm is an algorithm used in image processing to compute the medial axis skeletons of various geometric forms. And the way it works is you ignite a metaphorical grass fire around the perimeter of the object, and then you trace the flame fronts as they propagate parallel to the initial flame front and record the points where they intersect or where they meet in the middle, and that is the medial axis skeleton of the geometrical form. Now, actually, this algorithm implicitly encodes Huygens' principle that the waves propagate at right angles to the line. This is significant. So I propose a symmetry completion computational process through the medial axis skeleton. This is the reverse Grassfire algorithm. Starting over here with A, we begin with a 3/4 circular perimeter, and we ignite a grass fire that propagates inward toward the center. All of the flame fronts meet at the center. If you record the arrival of waves from various different points in the circle near the perimeter, there will be the early arrival of the first flame front and then a late ending of the last flame front. And the closer you get to the center, the shorter but more intense the time trace, and at the very circular center, you get an impulse function that records the perfect symmetry at the center of even a 3/4 circle. I propose that this is followed by a reverse Grassfire rebound of the waves after they collide with each other at the center, and they propagate outward for the same time interval that it took for them to propagate into the center. And when they arrive at that point, they stop and print the flame front, thereby completing the symmetry of the circular symmetry detected in the stimulus. This part of the process, reducing a circular arc to a point, is the principle of abstraction. This, taking the circular symmetry of the point and propagating it back out to the whole circle, is a process of reification, completing the pattern based on the symmetries detected in it. So, with the Canizza triangle, we can expect it to work something like this. Over here in this corner, we see two edges that intersect. So this suggests an occlusion, but it could actually be an occlusion this way, or it could be an occlusion that way. How can we tell which way the occlusion is? Locally, there's not enough evidence to determine that answer. This is how I propose the system works. First, you get a perimeter response around the perimeter of the partial circle, which propagates inward towards its center of symmetry. And there, the incoming waves collide with each other and radiate back outward again. And now, at this point, there's a stark contrast between the symmetry prediction that says I should be seeing a circular arc right here and the actual image where there's no arc there. And therefore, now it becomes reasonable to assume that this is the kind of occlusion we have. Now, if this same process was happening at the other two corners all at the same time, then the three completions will propagate into a center where they create the illusory triangle. The illusory triangle then radiates inward and finds its own center of symmetry, from which it bounces back outward. And where it strikes the circles, it completes there. So the whole figure resonates in and out as a unified gestalt. All right, now harmonic gestalt in 3D. Everything described so far in 2 dimensions extends naturally into 3D by the same essential principles. Imagine a 3-dimensional volume of point oscillators each point oscillating and radiating waves outward and establishing connections to other points. This would now produce an emergent global oscillation of the whole shape. Symmetry and closure promote resonance. So we now have translation, rotation, and scale invariant representation in full 3D. Using an intrinsic metric, using the ratio of the side lengths, and doing it now in full third dimensions in the nature of a Clifford algebra multivector. So now imagine that the front face of this cube is an input stimulus in 2 dimensions, and the volume of the cube is used to express the third dimension. So each of these points in the volume has its corresponding shadow here on the input screen, but the way it works is that the input points are given first, and there they tend to create an oscillation somewhere along their z-dimensional, 3-dimensional line, and these points are free to slide in and out along these rails until they reach a more harmonious configuration. For example, if the input stimulus consisted of these 4 points and another 4 points, and each one of these creates an oscillation in the volume, then these points will tend to slide along their rails, because in this way they can create a more harmonious configuration.
Here's my Harmonic Gestalt 3D program. This one also presents a stimulus screen where you can click to produce a stimulus spot. This time it also presents a 3-dimensional percept as an inverse projection into depth of this 2-dimensional spot. So wherever this spot happens to be in 2-dimensional space, this line here can be considered a probability density function of the probable location of this point in depth, given its location in 2D. Now in this simulation, we also have a slider here where we can adjust the value of that point in depth. Now we can add another point, and we get a musical tone. Here you can see a single frequency peak. And now we'll add an isosceles point in here, and we'll tune the location until it sounds harmonious. With 2 peaks in the Fourier spectrum. Now what we're going to do is we're going to adjust the depth of just this top point. And here we go. Moving inward in depth, you can see the slider change. And the dot moves. And if we give the sound a chance to catch up, it changes the tone. You see the 2 peaks of the Fourier approaching each other now. And now there's back to a single peak. What we have here, that's gone a little too far, come back a bit. And what we have here is an isosceles resonance, equilateral resonance in 3D to an isosceles stimulus in 2D, showing how this isosceles triangle can be viewed as an equilateral triangle in depth.
Okay, so we've discussed the forward problem. Given 3 oscillators in a equilateral configuration, we will produce a certain tone. Now the inverse problem is, how do we find that triangle? Beginning with the stimulus provided from the input, how do we do this? What this is the inverse optics problem for each edge of the triangle, we want to do an inverse reification of all of the possible lines at different angles and depths that could have projected to this line. So it's a field, a probability field in 3 dimensions, and on that probability field, we hope to discover some resonance. And here we have an isosceles resonance, as in the stimulus, but you could also hope for an equilateral resonance for the same stimulus, and that this one, being more harmonious, will be preferentially perceived. Now, this is an impossible computation unless implemented in a parallel analog wave-based mechanism. The fact that the visual system solves the inverse optics problem involuntarily, effortlessly, and instantaneously is direct evidence for a harmonic resonance representation in vision, because no other computational principle is able to reify an infinite range of possibilities simultaneously and in parallel. A couple of quick examples. Here's a diamond-shaped stimulus that can also be perceived as a square tile in depth, tilted in depth. And here is the inverse projection of the diamond. And embedded in that inverse projection is a perfect square stimulus that fits into the extruded diamond. Here we see another example. This time the same kind of diamond, but 3 of them that pops into a cube in perception. Here is the inverse projection of the edges in this stimulus, and here we can see the perfect cube that is embedded in that inverse projection. How do we know that cube even exists? We can see it right here, although we have to use our perceptual system to see the cube. Likewise, with this example, here we have a stimulus that's an ellipse, but it can be perceived as a circle in perspective. Here's the inverse projection of that ellipse, and embedded in that inverse projection is at least one circle and also another circle tilted at a different depth. And therefore, this is a bistable percept, where this can be seen either as a sewer cover in front of you or as a ceiling light above you. Those are the 2 alternative perceptions here. Of the infinite range of irregular ellipses embedded in the inverse projection, there exists 1 or more perfect circles tilted at just the right angle. Here we see another ellipse. This time it's wrapped around like a tin can stimulus. Again, we can do the inverse projection of these edges, and embedded in the inverse projection, there's a perfect cylindrical can embedded in that stimulus. So what is the evidence for this fantastically elaborate, highly speculative, and underspecified theory of vision? Well, here's the evidence right there. Do you not see it the way everybody else does? Perceptual modeling emphasizes that you can model the experience itself without regard to the underlying neurophysiology. You don't need to know the details of the neurophysiology to realize that the output of visual processing is a reified spatial image. Take a look at this example, a little bit too much to absorb in one glance, but observe how as you glance around the figure, different parts of it reify themselves until you get an impression of the whole. Is it valid to take the evidence of your own visual experience as evidence for the computational principles of perception? Because if it is, then it suggests that there's an explicit spatial field-like computational principle in the brain based on completion by symmetry. The principle of reification is perhaps the most underappreciated function of perception. A holistic global first principle of operation is highly suggestive of a wave-based resonance representation. Part 11, cortical maps.